you may use the chain rule to obtain the antiderivative of certain function. For example, by the chain rule, we know that the derivative of composition of the function is just the product of the derivative of the function evaluated at the gx here, multiplied by the derivative of g itself. Okay, of course, if we consider its antiderivative, then if I want to evaluate the antiderivative of f prime gx g prime x dx, then I may use the following chain rule: f composite g prime of x, and obviously the derivative of derivative is the function itself, and the derivative of a certain function is just the function itself. Simply this one, and of course I can write it as f g of x plus a constant. Okay, so that's the and you know that, but of course we will learn later on that this is a so-called the substitution method for simplifying the integral. Okay. All right. So that's the basic for antiderivative. Now let us consider the introduction to differential equation. Okay, so let us consider the introduction to differential equation. The idea is that if you, for example, in it's similar to antiderivative here, in the sense of we want to find a certain function whose derivatives is given. Okay, so that's the idea. For example, if you let's say if you have y equals to, let's say 3x squared, for example, then you know that dy dx equals to 6x. Okay, that's the basic stuff. But now the question is, if we start with dy dx equals to 6x, then the question is, what is the possible choice of y here? So that's the so-called differential equation. So the idea is that if you consider the derivatives or differentiation, then you start with the function, given function, and then its derivative. For the differential equation, you are given the derivative itself, okay? And then you have to find what is the function whose derivative is given. Of course, this is the, if we consider this kind of equation, then the solution will be an antiderivative, right? Okay, obviously, the answer to this question will be y equals to 3x squared, and we add some constant y plus e. Okay, so now let us consider, okay, several examples for differential equation. Okay. So for examples, find the solution, let's say, to the equation, let's say dy dx equals to 5x to the power 4, and then plus cosine of x, for example. Okay. So as I mentioned before, the derivative of the function is given, yeah, namely 5x to the power 4 plus cosine of x. The solution to this equation will be the function itself. What is the formula for y here? What is the formula for y? Of course, okay, before I continue the example, of course, you have learned this kind of problem in physics, for example. Let's say if you consider the moving particle, and then the velocity of the particle is given, then you want to know what is the position. Okay, what is the position of the moving particle? Of course, in this case, uh, the solution is not unique. In fact, there are many solutions to this equation. Okay, of course, but of course they are differed by constant. Okay, so in this case, to find the solution to this one, so the solution this equation will be y is an antiderivative of this one. So I take indefinite integral of 5x to the power 4 plus cosine of x dx here. Okay. And of course, by a linearity, I will have y equals to definite integral of 5x to the power 4 plus indefinite integral of what is it? Cosine x. Okay, so in this case, the integral of 5x to the power 4 is x to the power 5 because just add the power by 1 and then divide it by the new power. So namely x to the power 5. And then what is the antiderivative of cosine of x? Sine x, because the derivative of sine x is cosine of x. And then do not forget to add the constants. Okay. So if I consider the picture to this one, okay, so x to the power 5 plus cosine of x, okay, for example, this picture, then, okay, let's say I choose a constant equals to 1, okay, I have this one. Of course, if I replace the constant 1 by other constant, let's say -3, then the difference is that they just translation with the vertical direction. Okay, so just the difference is 4 here. So the blue one is obtained just by translating the red one for unit downward. Okay, and in general, there are so many solutions. For example, if you type any general C, let's say, if I turn this off first, then it's just take a look at the translation of the, for example, oops. Sorry. Okay, so I just take a look at the translation there. Okay. But the question is, if you are given the differential equation, then we have the so-called the solution with the some constant. Now, of course, we need to specify additional information, namely, if the solution pass through a several certain points. For example, if you have, let's say, here x to the power 5 plus cosine x minus 8 here, then probably not that good. Okay, let us take a look at another one. Okay. For example, here, if the solution pass through the point, let's say 0.732, 0, for example, then the solution is unique in the sense of you only have one C for the solution. For example, if you okay, or if I look for, let's say, this point, if you take x equals to 0, this moment, let's see, for example, when C equals to 2 and when c equals to 2 and 0 and x equals to 0, then you have, let's say, c is 3, so you get c equals to 2. So in this case, if I add additional information, for example, if y, let's say 0 equals to 3, so the meaning is that the, oops, sorry, I made a mistake. Sin x should be a sin x. Anyway, yeah, it's almost the same. If c equals to 2, then, sorry, this one. Okay, so c equals to 4, for example. So if I consider the following point, when x equals to 0, y equals to 4. When x equals to 0, y equals to 4. Then just simply substitute x equals to 0 and y equals to 4 there. So I get 4 equals to 0 to the power of 5 plus sine 0 plus c. So I will have c equals to 4. Okay. Therefore, the solution to the equation, okay, dy dx equals to 5x to the power of 4 plus cosine x with the condition, let's say y0 equals to 4 is y equals to x to the power of 5 plus sine x plus the constant c equals to 4 plus 4. Okay, so if you are given only the differential equation, then there are infinitely many solutions, okay, because there are many choices of c. But if you are given an additional information, something like this, then there is only one solution. Okay. Okay. Any question or comment? Okay, so in general, the differential equation is given, let's say, dy dx equals to f of x. Okay. Then the solution is just simply antiderivative of f is y equals to its antiderivative. Okay. Of course, with an additional constant. Okay. Okay, so let's say its antiderivative is f capital of x plus c. Okay. Of course, if you are given the initial value problem, namely the differential equation, with an additional information, for example, y at x0 is y0, then the solution is the same. The difference is that you need to find the value of c there. For example, the value of c can be obtained by taking x equals to x0 and y equals to y0 there. Then you get y0, then you get c equals to y0 minus f x0. Okay. So that's the two difference. That's for the differential equation. The solution is another derivative plus the constant. So there are infinitely many solutions because there are infinitely many t here. However, if you consider the same differential equation, but now you add an additional information. For example, when x equals to x0, the value of y0, or geometrically speaking, if the solution passes through the point x0, y0, then the solution is unique in the sense of you may take C, you may find particular value of C. Example, you take x equals to x0, put it here, and replace y equals to y0, then you will have C is y0 minus x0. Okay, so that's the the important difference between differential equation and initial value problem. Okay. Okay, any question or comment up to this point? Any question or comment? Is it clear? Okay. Now, of course, this is just the limited case of differential equation. There are many other cases. For example, the differential equation involves higher order derivative, but it can be solved. For example, if the left-hand side is the second derivative, for example, then we should find its first derivative, and then after finding its first derivative, then we find the function itself, function y. Similarly, if let's say this is a third derivative, then just look for the second derivative first, and then the first derivative, and then the function y solution. And of course, in that case, if you want to consider a particular solution, then you have to know more information. For example, the value of the function at certain point, the value of the derivative at certain point, and so on. Depends on the order of the derivative. Okay, so that's a general method for solving the differential equation. But of course, sometimes the differential equation involves, let's say, two variables. Let's say on the right hand side, f and x and y appear here. Okay. Of course, you cannot just take the derivative of the other derivative of this one, because this is not just the function of x. This is also a function of y, and y is the solution. So, for example, we cannot solve this differential equation for a general function f here, but we can solve it if the right hand side here is the product of a function of x only and then a function in y only. For example, if you want to consider, let's say dy dx equals to minus x over y here. So the idea here, if you have this differential equation, then you just cannot just take the antiderivative of this one, because here I have a function of y. This is the solution itself. So the idea for solving this type of differential equation is to separate the variable. And we call this method as the method of variation of variable. Okay. And to do that, let us recall the meaning of differential. Okay. If you have a function, let's say y equals to g of x, then the differential of y dy is just simply g prime of x dx, right? So if we consider that it's antiderivative, then we start with dy equals to g prime of x dx, then y is gx. So start from this equation, we separate the variable in the following sense. We collect the variable y only on the left hand side. So I start with y dy, and then the variable x only on the right hand side. So we have minus x dx. Okay, so you'll see that here on the left hand side, we are left with y variable. Okay. On the other hand, on the right hand side, the variable is only x. Okay, so that's the first step. Make sure that, okay, of course you can interchange the order, it does not matter. But let's say in the left hand side, we only have y. On the right hand side, we only have x there. Okay. Okay, so that's the first step. And then, okay, by using the concept of differential, we consider its antiderivative. So I will write it as indefinite integral of y dy. definite integral of minus x with respect to x. Of course, we can calculate this because it's the variable is y, and the integration or indefinite integral here is with respect to the variable y. Similarly, on the right hand side we have minus x, and then we just consider its antiderivative with respect to variable x. Okay, so we have integral y dy equals to integral minus x dx. So of course the integral of y dy is y square over 2 plus let's say the first constancy, and then on the right hand side I have integral of minus x. Its integral is minus x square over 2 plus, let's say, a second constant. Then we can write it as x square over 2 plus y square over 2 equals to c2 minus c1, and then we can write it x square plus y square equals to c, where c just 2 multiplied by c2 minus c1. Okay, so you'll see that start from dy dx equals to minus x over y. Then we can separate the variable. On the left hand side, the variable in y only. On the right hand side, the variable in x only. Okay. Write it as a differential there, and then takes it's an integral. It's an indefinite integral, or it's an antiderivative. Antiderivative y, antiderivative of minus x. And antiderivative of minus x is minus x squared over 2 plus a constant. And antiderivative of y is y squared over 2 plus another constant. And then we can simplify it into x squared plus y squared equals to some constant. Here where the constant is just the 2 multiplied by the difference of the initial constant. So, do you know what is the name of this equation? If c, let's say c is a positive, that's the equation of a circle centered at the origin of radius square root of c. And previously we know that from the implicit differentiation, start from the equation of the circle, then we can obtain its derivative as minus x over y. But now we start with the derivative first, and then we obtain that the solution is the equation of the circle. Of course, there are infinitely many solutions here, okay? Because there are infinitely many choices of C. Of course, the unique solution can be obtained if we have an additional information. For example, the circle, let's say, pass through a certain point. For example, if I consider the same differential equation, dy dx equals to minus x over y, for example, and then I add another additional information. Let's say if x at 0, let's say when x equals to 0, y 0, let's say equals to 1, for example, then you may find the value of c here. For example, x equals to 0, 0 square plus 1 square equals to c. So c equals to 1. So the solution to this is the equation x squared plus y squared equals to 1. Okay. Okay. Any question or comment? Any question? Comment? All right. So if there is no question, so let us try to do an exercise here. For example, we'll consider dy dx, let's say, equals to sine x over x squared. Over y squared, or 3y squared. So find the solution to this differential equation. Find the solution to the differential equation dy dx equals to sine x over 3y squared. Find the solution. So the differential equation dy dx equals to sine x over 3y squared. Please find the solution to the given equation. Dy dx equals to sine x over 3y. What is the solution? Yes. Okay, so what is the first step? The first step is to separate the variable x and y. So that's the first important step. This right in terms of on the left hand side is the y variable. The right hand side is the variable in x on. Okay, this will get the equation. Okay, so let us work on this problem. So the first step will be to separate the variable. So we have 3y squared dy equals to sine x dx. So that's the first step. And then, okay, consider its antiderivative. So it's antiderivative of 3y squared dy. And then it's antiderivative of sine x dx. Okay. So of course, the left hand side will be, what is the antiderivative? Y cube plus first constant c1. And then what is the right hand side? Negative cosine x plus constant, second constant. And then if we combine this, then we have y cube equals to minus cosine x plus okay, I just absorb the constant c2 and c1 to be one constant only. Okay, so the solution will be y equals to cube root of minus cosine of x plus a constant of c. Okay, of course, the value of c here is infinitely many. Okay, and to find the value of c, we need to impose additional information on certain value of y and x and y. Okay, for example, if let's say when if we add the condition, let's say y0 equals to let's say 2, then to obtain the constant, so this is the additional information. It can be any additional information. I just take the following information. For example, y at x equals to 0, the value of y is 2. For example, in this case, we have 2 equals to the cube root of minus cosine 0 plus the constant c. Obviously, here becomes 8 equals to cosine 0 is 1. So I have minus 1 plus c. So c equals to 9. So the solution to the equation dy dx equals to sine x over y square with the additional information y0 equals to 2 is, so the solution to this one is, its solution is what is the solution? Y equals to cube root of minus cosine of x, and then the value of constant is 9 plus 9. Okay. Any question or comment? Any question or comment? Okay. So, yeah, so I will summarize the discussion here. We have considered antiderivatives of a certain function, namely, if we are given a function small f, then we want to find a function f capital such that the derivative of f capital of x is the small of x. And we will abbreviate the notation by integral, indefinite integral fx dx. Okay, so it's an antiderivative plus a constant c. Of course, we can obtain an antiderivative of any power function like this. Just the formula is just writing x to the power n plus 1 divided by n plus 1 plus a constant c. And we can use the linearity of the derivative to obtain an antiderivative of polynomials, okay, any polynomials. And of course, we may also consider antiderivative of trigonometric function. For example, antiderivative of cosine x, because we know that the derivative of sine x is cosine x, then antiderivative of cosine x is sine x. Okay? By a similar argument, antiderivative of sine x is minus cosine of x plus a constant c. Okay? Of course, we may consider the derivative of secant square of x. And by using the chain rule, we may find an antiderivative of the following function, f prime of gx multiplied by g prime of x. Write this as the derivative of composite function by the chain rule. And then the antiderivative of the derivative of a certain function is just that function. So we have this one, and we see that this method is called a substitution method. And the application of antiderivative is to solve the differential equation. For example, if you are given dy dx equals to a certain function here in x only, then you may find its solution is just its antiderivative. Okay, it's antiderivative. Of course, if we impose or if we add an additional information, then we may get a specific value of the constancy. Okay. Okay. So we have a particular solution. Yeah. Of course, yeah, in general, we can write it as dy dx equals to f of x. Then the solution is just antiderivative of f, okay, with some constant, of course. And sometimes the differential equation can be written as follows. The left-hand side is dy dx. The right-hand side is some equation, some expression in terms of x and also y. So in that case, we may restrict our discussion to the case where the right-hand side is just a product or it's just a ratio of two functions in x only or in y only. For example, if you start with dy dx equals to minus x over y here, it's a function in x and y. But we can separate these two functions by writing y dy equals to minus x dx. This is the concept of differential. And then after writing the equation in terms of y variable and only on the left hand side and x variable on the right hand side, then we may take its antiderivative of its expression. Okay, antiderivative of y, antiderivative of minus x. Antiderivative of y is y squared over 2 plus the first constant c1. The derivative of minus x is minus of x squared over 2. Then we can simplify to get the equation x squared plus y squared equals to c. Or is the equation of a circle centered at origin of radius c, of radius square root of c. Okay. Okay. And in particular, if you have the information in some point between x and y, then you may obtain the value of the constant. Okay. And of course, we can repeat the argument for the following differential equation: dy dx equals to sine x over 3y squared. The idea is just separate the variable. Once you separate the variable, take its antiderivative for each function, and the derivative with respect to y, the derivative with respect to x, okay, one by one. And then on the left hand side, finally, you have the function in y only, then function in x only, then just simplify. Just simplify to following. So the solution to the differential equation up to this point is correct. However, there is an additional information, the value of x and the value of y. Then you should find the specific value of the constant c here. And just simply substitute the value of x, substitute the value of your y, then you get the equation in c, then find the value of, for example, if x equals to 0, y equals to 2, so 2 equals to cube root of minus cosine 0 plus c, yes, minus 1 plus c equals to a, and c equals to 9. Then the solution to this equation with the additional information here is y equals to cube root of minus cosine x plus 9. Okay, so that's the idea for differential equation. Later on in probably in the next 2 chapters or 3 chapters, we'll learn also this type of equation, but it involves the transcendental function, for example, exponential function e to the power x and natural logarithm function. But up to this point, we only consider for elementary function, algebraic function. Okay, any question or comment? Okay, if this is not the case, so let us take a break for a moment, and then we will consider the next topic about the integral. But now we will justify what is the meaning of the notation of antiderivative as an integral here, in the sense of we consider the definite integral. So this integral here is indefinite integral. So we'll consider the definite one, and then we will define it by using the limit of the Riemann sum. So and then we'll see what is the property of the integral, and go on to the later we will consider the relation between antiderivative and definite integral by fundamental theorem of calculus. Okay, so I will stop here, and then we'll have a short break and have a circle, for example. So one idea for calculating, of course, you know the formula. If you are given the radius, and then you want to know the formula of a circle, it's just pi multiplied by the square of its radius. But of course, we can do it differently. by using the approximation. Namely, if you consider, let's say, the square or rectangle inside the circle, then you will see that, of course, the area of a rectangle inside the square is smaller than the area of the circle itself. Okay, but of course, okay, there is an error there, and of course we can consider, let's say, if you draw the same circle, for example, then you may approximate the area of the circle here by, let's say, n polygon. For example, if you consider 1, 2, 3, 4, 5 polygon here, then the approximation is getting better. Okay? In the sense of the error of the area of a circle approximated by the here the number of the side here is 6. The polygon with n polygon with n equals to 6, then you will see that the error here is getting smaller. Of course, if you add the number of the sides of the polygon, then you will see the approximation is getting better. For example, if you consider again the polygon with the side number of side, let's say, increasing. Okay, for example, if you consider, okay, the number of the side, let's say, here is 1, 2, 3, 4, 5, 6, 7, 8, for example, then the area is getting close to the area of the circle. So the idea is that if you have a circle and then you have polygon and polygon, then if you increase the number n, then the area of the polygon will approximate the area of the circle. That's the intuitive idea. Of course, you may consider another approach. For example, if you have the same circle, but you may also approximate it from the outside in the sense of the polygon here, in the sense that the circle is inside the polygon. Okay. For example, this one. Then you will have also an approximation of the area of the circle. That's the idea of the approximation of the area. And we'll use this idea for calculating the integral. So if we start with the following observation, for example, if you have a function here, a constant function, let's say from 0 until 2, for example, and the constant function equals y equals to 3, let's say, then okay, y equals to 3, and we draw this up until 0 until 2 here. So here constant y equals to 3. So if we consider the area under the curve, I mean, if we consider the graph of the constant function and we consider the area, so this is simply just the area of a rectangle. Okay, so the area will be just simply 2 multiplied by 3 equals to 6. Okay, so we can do it. Okay, so this is the case of a constant function. Of course, if we consider a linear function, let's say, okay, so let's say consider a linear function. Again, let's say from 0 until 3, for example. And then the equation will be, let's say, y equals to x plus 1. Equation is y equals to x plus 1. So we have here have this one. Oops. Let's say, oops. Say y equals to x plus 1. Okay, so this is just the line. And the area under the curve is, so the area under the curve here is the area of trapezoid. Okay? And we know that how to compute the area of trapezoid. Just take the average of the parallel side here. So here I have the side length is 4. Here the side length here is 1. Multiplied by its length. Okay. So in this case we have the area will be 4 plus 1 divided by 2 multiplied by 3. So in this case you have 15 over 2. Right? So this is the area. Okay, so we have considered constant function and linear function, and then we calculate the area under the curve. Now, yeah, it's easy because we can just calculate it by the formula for, let's say, a rectangle or trapezoid in this case. But the things getting more complicated if we consider, let's say, a quadratic function. Okay, if we consider a quadratic function, 0, 1, 2, for example, 3. We consider a quadratic function, just 1, 2, 3, 4, example. Consider this. Then you want to consider this area. Then we do not have an elementary formula to calculate it. We do not have an elementary formula to calculate the area under the curve y equals to x squared. Under the area of the curve y equals to x squared, of course, we cannot just calculate it. Okay. Now, the idea is that we approximate the area just like the approximation of the circle. Namely, we calculate the area of a more elementary object by considering some approximation. So, in this case, let us rewrite the function and then consider the approximation. Okay, we consider the same picture here, but probably I will rescale this a little bit so that we have the bigger, so that we have the bigger picture here. Say 1, 2, 4. Okay, so let us consider this. So the idea is that we can approximate it by, let's say, if I draw a rectangle here, if I draw a rectangle, okay, for example, this one, and also this one, okay, I just simply approximate it. Okay, so the area, the green one, is approximately the sum of the area of the rectangle here. Okay, so of course, what is the area of the rectangle? The area of the rectangle, the first rectangle is 1, right? And then the area of the second rectangle, 1 multiplied by 4. Okay. So the area is approximately 5. But of course, you'll see that from the picture, the actual area is smaller than 5 because you have this remaining part, also the remaining part as well. Okay, so now, okay, so it's approximately 5, but in this approach, the area is actually less than or equal to 5. less than 5. Okay. Okay, so that's give us the information about the upper bound of the area. The area cannot exceed 5, okay, but it's around 5. Of course, let us refine the approximation. Okay, let us refine the approximation in the sense of we can refine it in the following sense. Okay, so let us divide now the interval 0 2 into smaller interval. Let's say if I consider the interval 0 half and then half and 1 and 1 half until 2, then do it similarly. I obtain, okay, now a smaller rectangle, okay, okay, and then okay, so this is the picture. Yeah, of course, this should be a 9/4. Then this is 1. So you'll see that okay, we may approximate the area under the curve, but now you'll see that the difference is getting smaller. Okay, let us calculate it. So what is the approximation of the area in this case? The area is approximately, so now we approximate it by the sum of the area of 4 rectangle. Okay, so what is the area for the first rectangle? What is the area of the first rectangle here? Its width is half. Its length is half and its width is a quarter, right? Because here the formula of this function is y equals to x squared. So if x equals to half, y equals to a quarter. So the area of the rectangle, the first rectangle is half multiplied by a quarter. And then the second rectangle, okay, the length is 1, the width is half, because this is, so half multiplied by 1. And the third rectangle, half multiplied by 9/4. Half multiplied by 9. The fourth rectangle, half multiplied by 4. If you calculate it, what is the result? 1/8 plus half plus 9/8. So 10/8, 5/4 plus, so you'll see 5/4. 5/4, 2/4, 7/4, 2. So that will be 3. 3/4, right? Can you calculate it? Yeah, about 3.75, right? So you'll see that the approximation is getting accurate in the sense of you'll see that previously the approximation is 5, but now the approximation is 3.75. 3 point, yeah, 3.7. Okay. And then we can define this by, again, okay, if we may repeat this process, if we consider a smaller interval, then hopefully we may get the more accurate approximation. Okay. Okay. Maybe. Oops. If you consider, let's say, for the previous interval, if you divide it into half, for example, 0 until 1/4, half until 3/4, 1 until 1/4, 1 3/4. Then again you will have approximately 8 rectangle. Okay, you will have 8 rectangles, and the area here. Okay, the area of the sum of the area of the rectangle is approaching the actual area, but the error, the difference here is getting smaller. So you can expect that the sum of the area of the rectangle is smaller than it's getting more accurate. Okay, so now, yeah, this is one approach. Of course, you may approach this if you consider the rectangle below or under the curve. Okay, so you may consider, let's say, the following approach. Okay, if you consider, let's say, of course, it's degenerate in some point. Let's say this one, but you may consider the rectangle as follows. Okay. 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 So the sum of this rectangle, you may approach in the some sense from inside the curve. Then you may see that the sum of the rectangle is actually smaller than the actual area. And previously, the sum of the rectangle is greater than the actual area. If you refine this in the sense of if you define the interval 0, 2 into a smaller interval, smaller and getting smaller, then you will see that it's defined, and then the sum of the rectangle in when the interval is infinitely many, then it approach the actual area. So that's the definition of the integral. So we will consider this. Okay, so the area can be written as area is actually, yeah, I will write this in formal way, and then we will consider the formal version of the integral. So it's in some sense is the sums of the area of rectangle, sums of the area of the rectangle when there are I will put the bracket infinitely many rectangle. Okay, so this is the intuitive idea. Now, okay, so now let us consider the general situation of this, namely, consider, okay, instead of x squared, we will consider a general function, any function, but we will consider it the non-negative one. Consider a non-negative function, fx greater than or equal to 0, on the interval a comma b. Okay. Let us focus on this one. The function is not only x squared, but any non-negative function. Then on the interval a comma b, we consider the partition of a comma b. The partition means we divide a comma b into a smaller interval. Okay, let's say the interval a comma b here, we'll divide it into n subintervals. For example, start with a equals to x0, and then the next one x1, x2, x3, so forth until, let's say, xn minus 1 until xn equals to b. Then, for example, if a comma b is interval 0, 2, then you can divide it into n subinterval. For example, n equals to 8, just divide this interval into 8 rectangle, for example. Okay, we call this a partition. Okay, partition of the interval a comma b is the set of p, where p is the set of the endpoint of a subinterval. Let's say x0, x1, blah 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 until xn. Okay? But we call this a partition of. Okay, so for the partition here, we have n subintervals. Okay, of course, the length of subintervals can be different. Okay, for example, if you consider, okay, so the length okay, of subintervals, okay, here, so the length of the subintervals, where is this? For example, if you okay, I will repeat the picture. Okay, let's say I will make it bigger. 0, x2, x3, for example, xn minus 1 till xn equals to b. Okay, so the length of each subinterval, we will denote it by delta x. Okay, so the first subinterval delta x1 is just simply x1 minus x0. The length of the second subinterval delta x2 is x2 minus x1, and then I will repeat it until the length of the n subinterval delta xn is xn minus xn minus 1. Okay, so in this case, the role of the length of subinterval will be the width of the rectangle. Now we will choose the length of the rectangle is as follows. So if we consider, let's say, a particular interval, let's say xi minus 1 comma xi. Okay. Okay. In the previous example, you may choose the length of the rectangle, either the value of the function to the endpoint, at the endpoint. Okay, but of course, I may choose any possible. Okay, I will erase this, and then, for example, if to give you illustration, oops, I may choose, for example, in the interval. Okay, probably I will, let's say, consider only for interval, for example. Okay. Oops. I consider here the interval. Okay, and then if I want to consider this interval 1, 2, then I may choose the rectangle as follows. Okay, this one, or I may choose this one. Okay, or I can choose any point in between 1 and 2, and I can choose any point in between 1 and 2. For example, let's say 1, it's this is just arbitrary, 1.3, for example. Then I want to make the rectangle as follows. So the length of the rectangle is determined by the value of the function at 1, 2. Okay. So here, this one is 1.69, because 1.3 square is 1.69, right? Okay, so I make the rectangle like this. Okay, so in this sense, the length of the rectangle can be varied. Okay, it depends on the choice of the sample point here. Okay, so if I go back to this situation, on the interval xi minus 1 until xi, I will choose a particular point, let's say xi bar, okay, is any point in between xi minus 1 and xi. Xi bar, of course, can be the endpoint, the left endpoint or the right endpoint. And then I will calculate f xi bar. Then the area of the rectangle in this particular setting will be f xi bar multiplied by delta xi multiplied by delta xi. Okay. Do you get it? Okay. Just consider this picture. So the sum of the area of the rectangle will be, okay. So the sum of the area of rectangle is, okay, so I start with the first interval, x0 until x1. Its width is delta x1, okay? And its length is f x1 bar. So fx1 bar multiplied by delta x1, okay? That's the area of the first rectangle. And then f x2 bar multiplied by delta x2 bar, so forth until f xn bar multiplied by delta xn. So that's the area of the rectangle. And previously, you'll see that if we take large n, then the area under the curve is it can be approximated by the sum of the rectangle. The sense of if we add the number of the interval, then the operation will be improved. So that's the idea. So I will abbreviate the summation by the sigma notation. Yeah, the sigma notation. I from 1 until n, f xi bar delta xi. And we call this as the Riemann sum. Call this as the Riemann sum, okay, of the function f on the interval a comma b. Okay? We call this as the Riemann sum. Okay. Now, the idea is that if I divide the interval a comma b into n intervals, and then I calculate the sum of the area of the rectangle by the following formula. Okay, this notation and this expression is the same, just the abbreviation. And we call this a Riemann sum. And if I take many subinterval, so in this case, I will take the limit as n tends to infinity, right? And you'll see that if we may say that the limit as n tends to infinity means the length of or the width of subinterval here is getting smaller. So delta x1 tends to 0, delta x2 tends to 0, delta x3 tends to 0, and delta xn tends to 0. And then the idea is that we will consider the largest value of the length of subinterval here as the norm of the partition. So the norm of the partition means here is the maximum value of delta x1 until delta xn. Obviously, if the largest subinterval, okay, if here the notation P here denotes the largest line of the subinterval, then if this one tends to 0, then all of this tends to 0. So, yes? This one? This is called the norm or the norm of partition. It's denotes the largest possible value of delta x1, delta x2, delta. So we have delta x1, delta x2, and delta xn. We choose the largest one. We denote this by the following. Then, after finding the Riemann sum, okay, then consider the limit as the norm of the partition P tends to 0 of the Riemann sum here. And if the limit here exists, okay, then f is called integrable. Is called integrable on the interval a comma b. Okay, f is yes.
Regarding the partition, like it's like the one is like the biggest value, like delta x1.
Yes.
Delta x.
Yes, exactly.
Is delta x1, delta x, delta xn like all are they equal or?
Okay, so in general they are not equal, but of course you may take the equal partition, namely if you consider if they are equal partition, so you have n subinterval, and then the length of the interval a comma b is b minus a. So if you consider the uniform partition, means the length of the subinterval is the same, then the length for each subinterval is b minus a over n. But in general, they are not the same. But if they are the same, then its length is b minus n over n. Of course, if the partition is if the length of subinterval are the same, then delta x1 is b minus a over n, delta x2 is b minus a over n. All of them are the same. Then of course the norm of the partition is b minus a over n itself, right? And the condition, the norm of p tends to 0 is the same as n tends to infinity, because n tends to infinity of b minus a over n is 0, right?
The delta x being equal becomes like arbitrary because like the n.
Yes, in a particular case. But for the definition here, we'll consider not necessarily equal length for a subinterval. But if they are the same, then the definition here is equivalent to taking limit n tends to infinity. Okay, so we say that this is integrable. And okay, of course, this limit is not so easy to calculate for a general f. But you may, for example, what happens if you take, let's say, a equals to 0 and b equals to 1, and f of x equals to, let's say, x squared, for example. Okay, what happened with this? Okay, so in this case, let us consider delta xi, and delta xi is the same. Okay, let us assume that now delta xi is the same. So let's say this one is b minus a over n. So this will be 1 over n. Okay. And xi bar to b equals to xi. Okay. So for example, in this case, if you consider x0 is 0, so what is x1? X0 plus delta x1. Delta x1 is 1 over n. So x1 is 1 over n. X2 is 2 over n, right? Until xn equals to 1. Then we may calculate the Riemann sum here the summation I equals to 1 until n f xi bar delta xi. But now delta xi is the same, so it's 1 over n. Xi bar here, where is in general xi bar equals to xi, so it's I square over n square, right? Correct. So in this case, I'm left with 1 over n cube. Summation now I equals to 1 until n I square. Okay. And what is the formula for the summation of I square here? That is n plus 1 to n plus 1 divided by 6, right? Okay, do you know this formula? Okay, so you may simplify this to be, okay, just divided by n and then calculate it, 2n square plus 3n plus 1 divided by 6n square. Or this is 1 over 3 plus 1 over 2n square plus 1 over 6n square. And finally, if I take the limit as, okay, so the limit as norm of the partition P tends to 0 is equivalent to the limit as n tends to infinity. The reason is that the number of the partition, the length of subinterval are the same. Okay, so if we have n subintervals, if the largest one tends to 0, then it's equivalent to infinitely many subinterval, right? They are equivalent. So finally, we just take the limit as n tends to infinity of the summation I equals to 1 until n f xi bar delta xi, and it's the same with limit n tends to infinity of here, this one. Okay, so that will be 1 over 3 plus 1 over 2n square plus 1 over 1 over 2n here, 2n, 1 over 6n square, and this will be 1 over 3. So that's why the conclusion here, fx equals to x squared is integrable on the interval 0, 1. Okay. And in this case, we say that the integral of 0 until 1 x squared dx equals to 1 over 3. Okay, because the limit, the value of the limit is 1 over 3. Okay. Any question? Of course, later on in the next lecture, we will learn that we do not need to calculate this one, okay? But but in the end, if we want to consider the integral from a until b fx dx, then we just simply use the fundamental theorem of calculus, namely finding the antiderivative at b, finding the antiderivative at a. So here, f prime of x equals to f of x. Okay. Yes. Yes. The reason is that if the, okay, so here for delta x1 is 1 over n, delta x2 is 2 over n, delta x3 is 3 over n, so forth, right? Yes. So we have the interval 0 and 1, and then we divide it into n subintervals. Okay, so the length is just the length of the initial intervals is 1, and then we have n smaller intervals, right? So the length for each smaller interval is 1 over n, right? N is the number of the partition or the number of subintervals. Just divide it into n subintervals. Then the length for each interval is 1 over n. So the largest here, the value of this one is also 1 over n. And if this one tends to infinity, tends to 0, sorry, then 1 over n tends to 0 or n tends to infinity. It's the same, right? That's why we can take the limit as n tends to infinity, replacing the limit of the non-p tends to 0. All right. Of course, okay, so here is the shortcut. In the next lecture, we will consider the shortcut. Integral from 0 until 1, x squared dx, for example. What is the antiderivative of x squared? 1 over 3 x to the power 3. So 1 over 3, 1 to the power 3 minus 1 over 3, 0 to the power 3. And that will be 1 over 3. And you'll see that the result is the same. Okay? Calculate by the Riemann limit of the Riemann sum and calculated by the fundamental theorem of calculus. So we'll learn in the next lecture about the fundamental theorem of calculus to simplify the calculation of the integral. Okay. Okay. Right.